All right, section 4.3. 4.3. You may have noticed we skipped 4.2. That was totally intentional because 4.2 deals a lot with those three variable equations we were looking at the end last time. I told you we were responsible for those. So we will not be doing that section. We're going to skip right over to 4.3. Solving systems of linear equations. Same thing we've been doing, only this time we're going to be using the matrix method. Some of you may know about matrices, others of you won't. But basically, a matrix is a lazy man's way of solving a systems of equations. It's essentially taking elimination and taking out the variables, and then solving via elimination. So that's pretty much what we're going to be doing. But let's take a look at what these matrices look like. A matrix is an ordered array of numbers, and yours should look a little different from mine for some reason. My notes just really don't like matrices, so I'll be handwriting most of this, but that is not, well, that is technically a matrix, it's just not a very common one. Instead, what you should see is more of a box kind of thing. So you've got these two big brackets on the side, and then you've got sort of a box, a bunch of floating numbers, right? So this is what we call a matrix. This would be a 2 by 2 matrix, right? So it's got 2 rows and 2 columns. That's why it's a 2 by 2. We're going to go into that a little bit more later. But basically, we're going to use these guys to solve systems of equations. Let's talk about that. We're going to be creating a very special kind of matrix called an augmented matrix. An augmented matrix takes equation systems like this, and it basically rewrites them as a matrix without the variables. Now, unfortunately, there is another typo. This should say 2x plus 6y and 5y. Sorry about that. So 2x plus 6y equals 9, and 3x plus 5y equals negative 10. And what we're basically going to do is take out the variables. So I'm going to go over here and say, okay, the coefficients of x, I'm going to put right here in this column. The coefficients of y, I'm going to put here in this column. And then I'm going to draw a little line to symbolize the equal part. And here's where I'm going to put the numbers. So I got to make sure my system is in standard form. I have to make sure all the x's are lined up, the y's are lined up, and the numbers are lined up, just like standard form dictates. And then I'm just going to write the coefficients in. So the coefficients of x were 2 and 3. And the coefficients of y were 6 and 5. And then the numbers were 9 and negative 10. And that's how you create an augmented matrix. You can ignore this thing down here. So there's our augmented matrix. Now what we're going to do is we're going to take this augmented matrix and we're going to solve it using something called row operations. And you may be thinking, oh my gosh, row operations, how could I possibly do this? But do not panic. These are the same steps for elimination. You can add any two rows can be switched, right? Just like we were with substitution and elimination, we can switch the rows. So I could rewrite this with the second equation on top. That's what it basically says. The second thing I can do is I can multiply any row I want to by a number, just like we were in elimination, right? Just like when I multiplied a 7 or a 2, same exact thing. I can multiply any row I want to by any number. And then in the last one, I can add any 2 rows to make something eliminate. That's essentially the same idea. So it's essentially we're just doing this in a box instead of in an equation. That's all we're doing, in a box instead of in an equation. When we start doing that, what the goal is here is obviously to solve the equation, but we want to get down to something called the identity. The identity matrix. The identity matrix looks like this. It's 1/2 of the augmented matrix. Most people leave off the augmented side, and what you want to see is 1, 0, 0, 1. It's basically a row of ones, or a diagonal of ones, and everything else is 0. So 0, 1, or 1, 0, 0, 1. Over here you'll have some numbers, right? And that'll tell us our solution. But this part right here, this green part, is what we call the identity matrix. The identity. It tells us the solution. It shows us that identity. So let's see if we can try that out. Let's take this system, and we'll solve it using a matrix. Let's solve using a matrix. This is one of my most favorite things because, like I said, it's the lazy man's way to do elimination. It saves you so much time if you know what you're doing. So as soon as you get these down, they're super fun. Alright, so let's start with our augmented matrix. We have the system x minus 3y equals 1 and 2x plus y equals negative 5, right? So let's go ahead and create a matrix out of that. And you know what? That's a little small. Let's write it a little bit bigger. Yeah, I don't like that one. Okay, so remember, I want to put my x's in a column, my y's in a column, and my constants in a column. So my coefficients here for x are 1 and 2. Coefficients for here or for y are -3 and 1. And my constants are 1 and -5. Alright, and then, therefore, we have our augmented matrix. Cool, we're starting to be lazy, right? Let's keep being lazy. What we want to do is get up to the identity, right? So we eventually want 1, 0, 0, 1. The fastest, most easiest lazy man's way of doing this is to go around this way. So I'm going to go around this way. I'm going to try and get 1 first, and then the 0, and then the 1, and then the 0. You, by all means, don't have to go this way, but I find that this is the way that proves the fastest. So let's start. Well, I've already got that first one, right? So this guy right here, he is already a 1. Awesome. I can check him off. Check. Got that one, right? Now I need this 2 to be a 0. If this was elimination, and I wanted that to be a 0, what I would do is multiply this first guy by -2, right? And add it so that the x is canceled. That's how I get 0. So that's just a little refresher on elimination. We're going to do the same thing. Same thing. I'm going to multiply this first row by -2. This is kind of the little script I use. The first row, row 1, sorry, by -2. And then I'm going to add it to that second row. I'm going to add it to row 2. Just like I would if it was elimination, right? So multiply everything in row 1. Multiply everything in the first equation, add it to the second equation so that the x is canceled. That's what I'm doing. But this time I'm being lazy and I'm not writing those variables down. So that's all I'm going to do. I'll make a new matrix. Now when I add this is where it's just itty-bitty little different from actually eliminating. When I actually do this, I'm using row 1, but I'm not losing row 1. You use it, you don't lose it, unfortunately. So I'm going to keep this row 1 exactly the same. Just because I'm using those numbers doesn't mean row 1 has changed, right? So up here in my little what did I do, I can say this only applies to row 2. Row 2 will be the only thing that's changing, okay? So let's look at this. If I multiply 1, so I'm going in the x column now, 1 by -2 plus 2 gives me a 0. In other words, 1, oops, sorry. Come on, there we go. -2 times 1 plus 2 gives me a 0. That's what I just did. I did this row calculation to the first column. I'll do it again. I'll do it with the y's now. -3 times -2, so that's where I'm doing this, times this guy. And then I'm going to add it to the bottom. So that would be +6, right, in row 1, plus my row 2 value would give me a 7. I'll do one more time with the numbers. -2 times 1 plus -5. So -2 times 1 is -2 plus 5 is -7. And I have my new matrix. And look, I don't really, at this point, I have a 7 and a -7, but that's not really important. The only thing I'm looking at is, yes, this first thing in my second row is now a 0. It matches my identity. Check. Okay, so check, check. Alright, next I'm going to swing around. I'm going to tackle this 1 right here. I'm going to find that 1. I need a 7 to become a 1. How can one get a 7 to be a 1? Well, I can multiply by anything or I could add anything. And adding is going to be just a little bit unnecessary right here. If I want something to be a 1, the easiest thing I'm going to do is times it by 1/7. So I'm going to times this second row by 1/7. In other words, I'm going to divide 7 by 7. When I times 7 by 1/7, it's the same thing as 7 divided by 7, and I end up getting 1. So I'm going to swing up here, build myself a new matrix. I'm going to go over here. I'm actually going to write this in pink to show that that's what we're doing and that's what we're getting. And then I'm going to say this applies only to row 2. So I'm going to take this row 2. My row 1 is going to still stay the same, absolutely the same. It does not change. I haven't done anything to row 1 yet. But in this second row, I'm going to times everything by 1/7, and I'm going to see what happens. 0 times 1/7, that's going to stay a 0. 7 times 1/7, that cancels. I'm going to end up getting a 1. Right, that was the whole point in the first place. Now I'm going to do the last one, negative 7 times 1/7. Well, the 7s are going to cancel, and I'm left with a negative 1. Awesome. Again, I don't really care what happens to the right-hand side of the equation. Excuse me. I'll care eventually. But right now, I'm just concerned with the fact that I get a 0, 1 on the bottom, so that I can check that guy off. And the last thing I want to do is make that last one a 0. This last guy up here in the corner, I need that negative 3 to be a 0. Alright, so now I'm going to do this same kind of thing. For any 0, you want to add a multiple. For any 1, you want to multiply by something. Okay? So let's see, how am I going to get this to 0? Well, if I was looking here in the elimination, I would say, okay, I need this one to be a positive 3, so that when I add it to a negative 3, it becomes a 0, right? The same thing with elimination. Same thing over here. If I want this to be a 0, I need that to be a positive 3. So I'm going to do 3 times row 2 plus row 1. And I'm only going to apply it to row 1. Alrighty, so 3 times this second guy plus the first guy will give me a 0. Let's go ahead and do that. So again, the row 2 is, so now it's row 2 that will remain untouched. Row 2 is not doing anything, but row 1 is going to change. 0 times 3, what's that? Well, 0 times 3 is going to be 0, right? And then plus 1 is just going to stay a 1. And that's good, because we didn't want that to change. 1 times 3, so this guy times 3, is going to be 3, plus that negative 3 is going to give me a 0. And then lastly, negative 1 times 3 is going to be a positive 3, plus 1 is going to be a 4. And we have arrived, check, at our identity matrix. We got the identity, great. So just a little recap. We switched the 2 to a 0 by multiplying by a negative 2 and adding. We changed the 7 to a 1 by just dividing by 7. And then we changed the negative 3 to a 0 by multiplying by 3 and adding it to the other row. We got our identity. You might be thinking, okay, that's all fine and dandy. I might need to practice that, but I think I get it. But who cares, right? How does this show me my solution? Well, if you remember from the get-go, this first column was our x's, second was the y's, and last was the constant. So this first column is still the x's, the y's, and the numbers, right? Our constant. So what this says now is that 1x is equal to 4, and 1y is equal to negative 1. Or in other words, x equals 4, y equals 1. So our solution is 4, negative 1. And that's it. Notice how little work that is compared to the last one. Now I know some of you are shaking your heads like, Miss K, you're crazy. This is not little work. This is so much more complicated. I just want to stick with my other one. Well, too bad, so sad. Because once you really figure this stuff out, it is so much less work. When you realize that this is just the the lazy man's version of elimination, it's going to save you so much time. So much time. And we're going to be working with these the rest of the chapter, so you kind of got it. Alright, cool. Pause the video now and ask any questions you have. If you don't have any questions, I would like you to try this problem all on your own. See if you can do the same thing, and then we will reconvene in just a sec, and I will do it with you. Okay, so I hope you've had time to try this one on your own. If you haven't, then I guarantee tonight's homework is going to be very long for you, but that's okay. That is your choice. We're going to start doing it together though. So I'm going to start by building myself an augmented matrix. I've got my x's and my y's and my numbers lined up, so I can go ahead and go over here, build myself a matrix. I've got 4 and 1, 5 and negative 1, negative 7 and 5, right? So that's all my coefficients and my numbers in my system. Alrighty, so we'll start off here. It looks like, remember what I'm shooting for, I can leave myself a little note over here, is 1001, right? That's what I'm shooting for. And it looks like I could start by changing that 4 with an addition or multiplication, but I noticed that there's a 1 in that second row. So what I'm going to do is actually switch these rows. Remember, that's a row up 2. I can switch the rows. Oops. So I'm going to redraw another matrix, and instead I'm going to put 1, -1, 5 on top, and I'm going to put 4, 5, and -7 on the bottom. All I've done is switch the 2 rows. Switch row 1, row 2. Awesome. And that gives me my first check mark. Check. Cool. Now I need the 4 on the bottom to become a 0. So in order for that to become a 0, I'm going to need to multiply and add. I'm going to need to do that eliminating thing. So if I think about it in terms of my system, right, how would I get that to be a 0? Well, I'm going to need that other one to be a -4, right? So I'm going to make that other one a -4. I'm going to do -4 times row 1 plus row 2. Just like with the elimination, if I do it to one of them, if I do it to x, I have to do it to y and the constants too. So that's why I can't just say -4x plus x, right? I would want to say -4 times the first row plus the second row. And that row is going to be changed. The row that's going to be changed is row 2. So let's go ahead and do that. And that'll all be in blue. All right. Got myself a new matrix now. That first row is not being changed, so it stays all by itself, stays the way it is, right? But that second row, I'm going to think, okay, -4 times 1 plus that 4 is going to give me a 0. -4 times this guy right here. So -4 times -1 is going to be a +4, plus the 5 on the bottom is going to be a 9. And then lastly, -4 times 5 is -20, plus -7 is going to be -27. All right. Wow, 9 and -27, those are ugly. But guess what? I don't care, right? I don't care right now what those are. I'll deal with them later. All I care is that this guy on the end ended up being a 0, so I can go off and check that off, right? I don't care right now, just like I didn't care that I ended up getting the 300s in the last section. All I care about is that being a 0. Alright, moving on. Now I care a little bit, because now I need this 9 to become a 1. How was I supposed to get something to become a 1? Well, how did I get a 7 to be a 1 in the last example? Excuse me. I had to multiply by 1/7, right? So I divided by 7 in a sense. I'm going to do the same thing here. I'll multiply by 1/9. Row 2 to row 2. And the only thing I'm going to change is row 2. Then I can go up here, draw myself a new matrix. Again, row 1, I'm not going to touch. I'm not going to touch it at all. Row 2, I'm going to multiply everything by 1/9. Well, 0 times anything stays a 0. 9 times 1/9 ends up being a 1. That's why I wanted to do it in the first place, right? And then -27 times 1/9 is the same thing as -27 divided by 9, or -3. Alright, cool. And I got that one to be a 1. Check. Sweet. Do I care that the other side is a 5 and -3 so far? No, not really. Do I care that the other row still doesn't have a 0? Not at this point. But right now, all I wanted to happen actually happened. Alright, the last thing is I need this one to be a 1 or 0. So now I need this last 0, this -1 to become a 0. In order to do that, it looks like I can just go ahead and add the rows. Remember how sometimes in elimination, you are already set up so that when you add, they eliminate? That happened here. I already have it set up that I can eliminate. So I'm just going to do row 2 plus row 1. And I'm going to apply it to row 1. And what I end up getting is, well, I didn't change row 2 this time. So row 2 is still 0, 1, -3. But when I add those, I get 0 plus 1 is equal to 1. 1 plus -1 is equal to 0. And -3 plus 5 is equal to, +2. And I got my last part of the identity matrix. Yay, we did it! Woohoo! And so now I have my answer where x is equal to 2, y is equal to -3. In other words, 2, -3. Ta-da! Alright, so notice it's kind of the same pattern, like throughout all of them. If you need a 0, you do this multiplication thing. If you need a 1, you multiply by 1 over what you need, right? And that's really what it comes down to. But I'm not going to say that happens every single time, because you notice it was easier when we just wanted to switch. But you know that you can always use that option. You can use the switching. The addition gives you a 0. The multiplication gives you a 1. And that's usually the pattern it follows. Alrighty, cool. If you have any questions, ask them now, because we're going to go on to three variable systems. Again, you will not be responsible for this, but I'm just going to show you how one works, because they get kind of cool. Alright, but pause right now if you have any questions at all. Alrighty. So, 3 variable systems, same thing, right? Just like you saw that elimination, you can do that too, since this is easy. This is like lazy man's elimination. It's the same thing. So let's go ahead and do that. I'm going to start with my augmented matrix. Just pull out all of the stuff. It's going to be quite a big augmented matrix. That's not close enough. Put that there. Okay. So I've got 1, -1, I guess I'll do the x's. 1, 3, 1. 1, 3, 1. -1, 3, 3. 5, -1, 2. And then my constants are -6, 10, and 5. Alright, cool. So now I'm going to start this off. I'm going to do the same thing. My identity is going to be a little bigger. I'm going to have a row of 1s, everything else be 0, right? Everything else is 0. But I'm going to go around in sort of a spirally inward pattern. But it's the same idea. Go around in a spiral, okay? So I'm going to go here. Looks like that one is already a 1. Sweet. Check it off. Check. Didn't need to switch, didn't need to add. We're good, right? Alright, got that one. So the next one I'm going to do is that 3. I need that 3 to become a 0. Anytime I need a 0, I'm going to end up adding a multiple, right? So I'm going to work with, just like with elimination of 3 variables, I have a little bit more choice here, right? I have more than another row to consider. So I think I'm going to choose row 1 and row 2. I'm going to do 3 times, using green, 3 times row 1. I'm sorry, -3 times row 1 plus row 2. And I'm going to apply that to row 2. So again, you are not responsible for this because there are quite a few more steps, but it's the same thing. It's the same thing. So by paying attention now, you're really reiterating these steps. I need a 0. So I multiply this first row by -3, just like I would in elimination, to get those to cancel out, those x's to cancel out. So that's what I'm doing here. When I do that, I end up with row 1 stays the same. Row 3 stays the same. And I end up with -3 times 3 is 0. -3 times -1 is going to, oops, my apologies. Back up here, -3 times the -1 plus the 3 is going to give me a 6. -3 times 5 is -15, minus 1 is going to be a -16. And last but not least, that's a -60 plus 6 is 20. I'm sorry, that'd be -18 plus or positive 18 plus 10 would be 28. All right, my numbers are getting a little bigger, but remember that's okay. That's okay. It's the same rule. All right, and I can check off that 0. Boop. Check. All right, now I need to do, let's see, I did 1, 2, 3. Now I need that last one to be a 0. So another addition. I'm going to do -1 row 1 plus row 3. So in other words, I'm just going to negate the first row and add it to the second row to get those 1s to cancel each other out. That's what I'm going to do. All right. Set myself up another matrix. Since I'm not changing, and I'm actually going to put that in row 3, right? Since I'm not changing row 1 or 2, I'll keep them the same. 0, 6, -16, and 28. And then the last row becomes, let's see, -1 plus 1 is 0. Negative plus times negative is 1, plus 3 is 4. negative 1 times 5. So what I'm doing over here is I'm doing negative 1 times 5 is negative 5, plus 2 is negative 3. And then negative 1 times 6 is 6, plus 5 is 11. Fabulous. And we have that 0. Check. Now I'm going to wrap around the bottom. I want to make that 4 into a 0. I don't want to go to pink again. Let's do red. So I want the 4 to be a 0. Every time I want a 0, I want to make sure I add by something. Sorry, one sec. Okay, I'm actually going to take a slightly different step because it might be easier to actually go this way. This is not common, and nor are you responsible for knowing this, but I'm actually going to go that red pattern. So still the 1, 2, 3 we have, but now I'm going to actually change the 6. This is going to be my next thing. The only reason for that is because the 6 is bigger than the 4, and because that I don't want to get into fractions, I don't want to get into many fractions, I should say. I'm going to change that. I'm going to change that first. So here's what I'm going to do. I want that to be a 1, right? So still go to our identity. Oops, 1, 1, 1, 0, 0, 0. Check, check, check. Now we're going to actually loop up here and get that to be a 1. So in order to get this 6 to be a 1, I'm going to multiply the second row by 1/6. And I think I'm going to head up here. I'm going to head up here to do that. And we're going to draw ourselves a new matrix. Sorry about that. Alright, so row 1 and row 3 are not going to be affected, so they will stay the same. 1, negative 1, 5, negative 6, 0, 4, negative 3, and 11. But if I multiply the second row by 1/6, I end up with 0, 1, and then negative 8/3. Like I said, many fractions, there's still 1, and 14/3. 14/3. Alright, I got that to be a 1. Awesome. And that was to row 2. Okay, cool. So now from here, I think I'm going to go get rid of that 4. I'm going to get rid of that 4 because it'll just be easier since that's a 1. So what I'm going to do is multiply, I guess I'll write it down here, negative 4 row 2 plus row 3. That way that 4 is going to go to a 0. Alright, let's go ahead and do that. Again, so that's going to be applied to row 3. So row 2 and row 1 are now unaffected. 0, 1, negative 8/3, and 14/3. Those all stay the same. I end up with 0 times negative 4 plus 0 is going to be 0. I end up with another 0. And then the fraction part ends up giving me a 23/3 and a negative 23/3. As you can tell, this is why you're not responsible for 3 variable matrices, because they can get into fractions a lot. I'm not saying it doesn't happen in 2 variable matrices, but it's not as often, and I just don't want you guys to deal with that. So, especially when you're first learning these. Alright, cool. So I've got that. Now I check off that one. So check and check. And we're going to head over to this 23/3 becoming a 1. In order for that to happen, we're going to multiply this guy by a 3 over 23 to row 3. And that's nice and easy since most of the things are 0. Our other rows still remain the same. 0, 1, 8/3, 14/3. And we end up with 0, 0, 1, and negative 1. But so I just flipped the fractions there, right? Since they happen to be the same fraction, I knew they would end up both being 1. That's a happy coincidence. All I really cared about, though, was getting that 23/3 to a 1, so I multiplied it by a 3 over 21. Alrighty, we're almost done. Getting there anyways. And Whoa. This is annoying. Okay, anyways, we keep going with this pattern, da-da-da-da-da, and we end up, since I'm running out of room, we're going to kind of kill it here, but we end up getting 1, 1, 1, 0, 0, 0, 0, 0, 0, and then on the right-hand side, a 1, 2, and a negative 1. So this tells us that our three-dimensional solution would be 1, 2, and negative 1. But you can see how one can keep going all the way around and end up getting the correct solution. Alright, cool. Again, you will not be responsible for that, but it does work for three-variable systems, and it can be very useful. These are used a lot in Pixar animation, so if you ever have a matrix, mostly the transformations are used in the Pixar animation, but sometimes these are used for Pixar animation, also for large data files with accounting. So if you ever go into accounting, you'll probably see these again. If you ever go into sales or anything like that with business, you'll probably see these again. At that point, you can deal with the three-dimensional ones. I've gone up as far as 54-dimensional ones. Yes, those exist. It's just a very, very large matrix, and it can be done. Usually it's done by computer anyways, though. So the solving of the larger ones is not really a vital thing to know. But solving the smaller ones, that is definitely important, definitely important. Let's talk about a few of the smaller ones again, and seeing what happens when you get something called an inconsistent system. Inconsistent system. This is the same thing as those infinite solutions and no solutions. They have the same results. Because this is just another way to solve a system, it's just another, that's the same thing can happen. You can still end up with a system that does not work, right? So let's see which one this would be. Whether it has infinite solutions or no solutions. We'll start with an augmented matrix. Right, so we make a matrix out of these guys. We have our x variables 2 and negative 6. Negative 3 and 9 are our y variables. And then 8 and positive 4 are our coefficients, our constants. Alrighty, let's solve this just like we would any others. Pretend it's not anything special. We're shooting for 1, 0, 0, 1, right? If I need that 2 to become a 1, then I'm going to need to multiply it. This is a little tricky because my other one's not already a 1, right? We've seen a lot today where it's already a 1. So how would I do that here? Well, here, if I needed the x's to go away, I'd multiply this one by 6 and this one by 2. I'm going to do the same thing. If I need this one to be, if I need the top one to be a 1, I'm so sorry, it needs to be a 1. I don't know what I'm talking about. Just kidding. We don't need to do that because it doesn't need to be a 0. It needs to be a 1. JK, LOL. In order to get a 1, I just multiply by 1/2. 1 over 2 to row 1. And that becomes a 1. I like to complicate things sometimes. Anyways, so I need that 2 to become a 1. I'll multiply everything by 1/2, or I'll divide everything by 2, right? So I can divide everything by 2. I end up getting the same second row, right? I'm not dividing everything by 2, just that first row, right? Just that first row. So I end up getting 1, negative 3/2, and 4. Divide everything by 2. Alright, now I need that 6 to become a 0. So this time I'm going to need to add. So I'm going to do 6 times row 1, and I'm not going to use blue again, let's use purple. 6 times row 1 plus row 2 applied to row 2. So now row 1 is going to stay the same, right? Row 1 is going to be left alone. 1, negative 3/2, 4. 6 times 1 minus 6 is going to be 0. 6 times negative 3/2, well, 6 times negative 3/2, well, let's not do it there. 6 times negative 3/2 would be 6 times 3, negative 18, over 2, which would be negative 9, right? So 6 times negative 3/2 is going to be negative 18/2, or negative 9, right? Add that to row 2, so plus 9 is going to be 0. And then we have 6 times 4, which is 24, plus 4 would be 28. And, uh-oh. What just happened? Anyone see it? this just happened. When you get a row of all zeros, or at least zeros on one hand side, there is no possible way for me to now make this guy a 1. Because anything times 0 is going to end up being what? A 0, right? So there's no possible way to get 1. Which means we have an inconsistent system to get 1. Which means that these two are in fact parallel lines. Remember, if you end up with something that makes sense, if we got a 0 on the other side too, we would have had the same line, right? 0 plus 0 equals 0. That would have been the same line. But here, these are two parallel lines. They have no intersection. Because they have no intersection, they have no solution. No solution. So that can happen from time to time if you end up with a row of zeros and on the other side you end up with a number. Remember, it's infinite solution if you end up with something that looks like this. 1, 2, 3, 0, 0, 0. Right? So if you end up with 0, 0, 0, then you end up with infinite solutions. Those two things can happen. The same exact reason as our systems, because remember, this isn't a whole new concept. This is just another way to solve a system. Alright, I've left you with a lot of information today, so go through. You're going to want to memorize these row ups as fast as you can, but it's really easy because it's just the elimination method, right? As long as you can do that, practice these guys, and you will be fine. Alrighty, we will reconvene when we do 4.4.